Pluto is a far-off and secretive planet that was once a part of our nearby planetary system. However, recent shocking revelations by leading astrophysicists Neil deGrasse Tyson and Kaku have brought Pluto back into the spotlight. They suggested that this icy world is on a potential collision course with Neptune. But how could this actually happen, and what might be the consequences of such a colossal event? Are we witnessing a bewildering cosmic anomaly, or is there something more to this impending celestial catastrophe? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet, remains a subject of interest and study in the vast universe. According to recent predictions from leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Kaku are raising alarms about a potential catastrophic collision between these two planets, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit, and since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is characterized by its highly elliptical shape, straying far from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, tilted at 17 degrees to the ecliptic plane. This steep inclination and eccentricity add layers of complexity to its orbital arrangement. Perhaps one of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The examination of Pluto's orbit began shortly after its discovery. Initially, astronomers sought to understand its unique path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit, despite these complexities, is evidence of the intricacies of celestial mechanics, the three-body problem in space. Determining how three objects in space, such as Pluto, Neptune, and the Sun, move and influence each other with their gravity is key to understanding this stability for Pluto. This problem reveals how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex interplay. Terms such as non-synchronous libration, orbital precession, and VZK wobbling are crucial to this puzzle, as explained by astrophysicists. What keeps all planets in their orbits is non-synchronous libration. In the case of Pluto and Neptune, this term essentially means that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is critical in preventing their orbits from intersecting. Orbital precession, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, adding an extra layer of protection from potential collisions. Another key factor in this situation is the VZK wobbling, named after three researchers, Vladimir Zell and Kai, who studied how objects move in space. It involves how three celestial objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This gravitational interaction influences how they move. For Pluto, the VZK wobbling helps explain why its orbit near the Sun is so unusual despite its seemingly chaotic orbit. This wobbling helps keep it moving smoothly over extended periods. The VZK wobbling shows that although space may seem wild and unpredictable, patterns and rules maintain some level of order. These forces help stabilize Pluto's orbit, ensuring that it doesn't collide with Neptune or drift off course. The three-body problem is critical to understanding how these orbits evolve due to the gravitational interactions among celestial bodies. Studying this helps us learn more about Pluto, our solar system, and even distant galaxies and their stars. Mathematical simulations in the late 1980s revealed that despite its stabilizing properties, Pluto's orbit is highly sensitive with minor changes in initial conditions, leading to significant differences over centuries. However, these peculiarities of Pluto's orbit have been found to maintain stability over very long time scales. Recent automated analyses have helped us understand how the giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit around the Sun. Neptune has a special relationship with Pluto where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune is not alone in this effort. Jupiter's gravity also plays a monumental role in stabilizing Pluto's orbit, as does Saturn. These studies demonstrate that Jupiter's immense gravity is strong enough to keep Pluto on a steady path for a long time, possibly even for millions of years. Thus, Neptune, Jupiter, and Saturn seem to work together to ensure Pluto continues to move safely through space without encountering trouble. These phenomena are crucial to keeping everything in place in the cosmos. Without these stabilizing factors, the solar system as we know it would be a much more chaotic place. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction with other celestial objects. For Pluto, especially with discussions about its potential collision with Neptune in the future, understanding its orbit is vital. This provides a clearer picture of the dynamic nature of the nearby planetary system. The case of Pluto shows that even the most seemingly unstable orbits can reach a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the strange nature of celestial bodies, and Pluto's orbit is a perfect example of this oddity. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight changes in the dwarf planet's position or velocity can significantly alter its long-term orbit. Using automated simulations has been immensely helpful for scientists in understanding how Pluto moves through space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune interact gravitationally. By tweaking small details in the simulations, astrophysicists can observe how even minute changes can have a huge impact on Pluto's trajectory. In the late 1980s, these simulations revealed something fascinating about Pluto's orbit. Despite having stabilizing features like non-synchronous libration and orbital precession, its orbit can still be inconsistent and unpredictable. A slight change in Pluto's initial position or speed can result in a completely different orbit after just a few years. Yet despite this apparent chaos, Pluto's orbit remains stable over vast time. Scales like billions of years imply that Pluto's excursion around the Sun has a sort of order to it, despite the fact that it appears wild at first. anticipating divine movements, especially when they involve irregular orbits like Pluto's, is a gigantic challenge. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties, while mathematical models provide excellent tools for understanding and predicting the future movements of celestial bodies. They also highlight the limitations of our predictive capabilities. These models heavily rely on the precision of initial conditions, and any small error or distortion can lead to vastly different outcomes, making accurate predictions a daunting task. Beyond the chaotic nature of planetary orbits, Pluto reminds us of the ever-changing and dynamic nature of the universe. While we've made tremendous strides in understanding space, Pluto's case serves as a reminder of how much of the universe remains unknown. Grasping the gravitational effects of the giant planets on Pluto's orbit provide significant insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can significantly influence the stability and trajectory of other bodies within the system. So why are leading astrophysicists recently raising concerns about a possible collision between Pluto and Neptune? Despite the intricate forces working to prevent such an event, Neil deGrasse Tyson, a prominent astrophysicist and a key figure in advancing cosmology, offers a unique perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, offers sharp analysis on the evolving nature of celestial mechanics and the public's interest in the overlooked corners of space. Tyson's stance on Pluto's reclassification is based on the ever-expanding knowledge of our solar system. He views the renaming not as a diminishment but rather as a necessary adjustment to our growing understanding of the diverse bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a reminder of how much there is still to discover in space. The interest in these questions keeps the study of space exciting. However, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the fate of Pluto's orbit suggest that we may still have some mysteries to uncover. Will Pluto collide with Neptune, or is this simply another moment of confusion in the ever-changing universe of space? Only time and further research will tell. For now, we are left with a deeper curiosity about how little we truly know about our own solar system. We continue to study these celestial phenomena with the aim of uncovering more of the secrets that lie beyond. The possibility of a Pluto-Neptune collision raises yet another question about the enigmatic and captivating universe in which we exist. The potential for a catastrophe between Pluto and Neptune raises fascinating questions about the dynamics of the solar system as it challenges our conventional understanding of planetary stability. That two celestial bodies with such vastly different characteristics could collide is both unsettling and intriguing, especially given the current relative stability of their orbits. Pluto is situated in the outer reaches of the solar system, far from the major planets, while Neptune is a gas giant with a strong gravitational field. The implications of such a collision would be immense for how we understand gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains various elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere composed primarily of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas giant, is made mostly of hydrogen, helium, and other lighter elements with a deep, dense atmosphere. A collision between such bodies would drastically affect their structure and behavior, potentially creating an event observable across vast cosmic distances. What makes this hypothetical collision particularly fascinating is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only factor at work. Jupiter, the largest planet in the solar system, is another key player. Jupiter's enormous mass, strong gravitational field, and stabilizing influence on Pluto's orbit prevent it from straying too far into Neptune's domain. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune highly unlikely. However, despite the apparent safeguards, ongoing research has shown that the relationship between Pluto and Neptune is not as simple as a clear collision course. The gravitational resonance between the two planets, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a sort of celestial lock that prevents them from coming into direct contact. This resonance, often described as a gravitational dance, ensures that whenever Pluto moves closest to Neptune's orbit, Neptune is always positioned far enough away to avoid any potential collisions. It is a remarkable example of how celestial bodies can maintain harmony in the chaotic environment of space. The importance of this mechanism cannot be overstated when considering the complex interactions between various planets and moons, particularly in the outer solar system, where the distances and gravitational forces are vast and varied. However, the future of this delicate balance is not set in stone. The outer solar system is a dynamic place with the potential for changes occurring over long periods. Small gradual changes in the positions or velocities of these celestial bodies could eventually disrupt the resonance, leading to unpredictable outcomes. Such a shift could be caused by an external force, such as the gravitational influence of an as yet undetected planet or a passing star, or by an internal event such as the slow decay of the orbits due to tidal forces. Continued observation and study of Pluto, Neptune, and the surrounding bodies in the outer solar system are necessary to better understand the long-term stability of the system. As technology advances and new tools are developed to observe the farthest reaches of our solar system, scientists will be able to refine their models and gain a clearer picture of how these distant objects interact with one another. With new data, we may uncover more about the delicate balance that prevents a collision between Pluto and Neptune, or perhaps discover new forces at play that could alter their relationship entirely.